Hello everyone, welcome to Manasiya's classroom. Today we are discussing about an asymptotic notation Big O. Big O notation is used to express the efficiency of an algorithm in a general way. In algorithm analysis, we are not mainly interested in exact execution time because execution time depends on system speed, programming language, compiler, and hardware. When searching for a student's name in a list, the number of checks increases as the list size increases. Big O notation focuses on this growth in operations rather than the exact time taken. For example, if input size becomes double, triple, or very large, Big O helps us understand whether the algorithm grows slowly, moderately, or very fast. Big O notation is one of the most important concepts in algorithm analysis. It tells us the order of growth of an algorithm. Here we do not calculate the exact number of seconds. Instead, we study how the algorithm behaves as the input size increases. So Big O is mainly used to compare algorithms based on their growth rate. The same program may run faster on one computer and slower on another computer. So measuring only execution time is not reliable. That is why we express algorithm efficiency using input size n. If the number of operations is written as a function of n, then Big O helps us identify the most important part of that function. In algorithm analysis, n represents the size of input. For example, number of elements in an array, number of nodes in a tree, or number of records in a file. The function f of n represents how many operations are performed for input size n. Sometimes f of n may be complex, like f of n is equal to 3n square plus 5n plus 10. But for large values of n, the term n square dominates the growth. So the complexity becomes order of n square. Big O focuses only on the dominant term. Dominant term means the term that grows fastest when n becomes large. For example, 5n square plus 3n plus 20. Here, n square grows faster than n and constant value 20. So we ignore 3n, we ignore it, and we ignore the constant value 20 also. Also, we ignore the multiplier 5. Therefore, 5n square plus 3n plus 20 is equal to order of n square. Mathematically, we say f of n is Big O of g of n if and only if there exist positive constants c and n naught such that 0 is less than or equal to f of n is less than or equal to c into g of n. That means f of n is always less than or equal to c into g of n for all the values of n naught where n naught is, for all the values of n where n is greater than or equal to n naught. Okay, here c is a constant value, positive constant value. N naught is the starting value from where this condition is true. So this means after some point g of n acts like an upper boundary for f of n. So we need to remember this term very importantly, upper bound. So this Big O always tells us the upper bound. Okay, so suppose if we take a graph like this. here I am drawing a function, some g of n. This f of n, starting it ups and downs, but it is always, after some point, it is always less than c into g of n. So the point where this value or this condition is being true, this point is known as n naught. So after this point, always this f of n is being less than or equal to c into g of n. Okay. So upper bound means maximum growth limit. Big O tells us that the algorithm will not grow faster than the given function after a certain input size. So when we say an algorithm is order of n square, it means its growth is bounded above by n square. It may take less time for some inputs, but in general, its growth will not exceed that order. Think of it like a speed limit on a highway. If the speed limit is 80 km per hour, your car may travel at 40, 50 or 70 km per hour, but it should not exceed 80 km per hour. Constants are ignored because Big O studies long-term growth, not exact counting. For large input sizes, constant multipliers do not change the category of the growth. For example, 4n and 100n both increase linearly. So both are written as order of n. Next, similarly, 50n square is written as order of n square. Algorithms are classified into different categories based on their growth rate. Order of 1 is the most efficient category because it does not depend on input size. This one. And order of log n grows very slowly, logarithmic time. Order of n grows directly with the input size n. Order of n square and order of n log n grow much faster, and order of 2 power n grows extremely fast and becomes impractical for large input sizes. So this order is very important. As we move from left to right, the complexity increases. Constant time is the best. Logarithmic time is also very efficient. Linear time is acceptable for many problems. Polynomial complexities like order of n square, order of n cube may become slow for large input. Exponential time is usually very expensive. An algorithm may behave differently for different inputs. Best case means the algorithm takes minimum time. Worst case, the algorithm takes maximum time. Average case means expected time for general input. When we simply write Big O, usually we refer to the worst case complexity because it gives a safe upper limit. So here we want to prove that 4n square is equal to order of n cube. So according to the definition, f of n is always less than or equal to c into g of n. So let f of n is equal to 4n square. G of n is equal to n cube. So we can write 4n square is always less than or equal to 4n cube for all n greater than or equal to 1. So we can take this 4 as c. And n naught, this 1 we can take as n naught. So therefore 4n square is equal to order of n cube. Okay. Next one more example. 400 n cube plus 20 n square is equal to order of n cube. In this expression, the highest power term is n cube. The term 20 n square grows slower than 400 n cube. So for very large values of n cube dominates the entire expression. So we ignore lower order term and constants. So we ignore n square and we ignore any n terms and constant terms. So for very large values, n cube dominates this entire expression. Therefore, 400 n cube plus 20 n square is equal to order of n cube. So this 400 we can take it as C, and n naught is equal to 1. So always 400 n cube is less than or equal to n cube order of n cube. Okay, it is equal to. See here dominant, we always, what shall we do? I'll tell you a trick here. So whatever f of n is given to you, in that f of n, you always choose the highest power term. Ignore the constant value, ignore the multiplier value, and you always choose this highest power term, and you write it as order of that highest power term. Suppose in your expression, if you have the highest term as n cube, you can write the big O notation as order of n cube. If your expression has n square term, then you can write it as order of n square. Like that. You can blindly choose the highest power term by ignoring this multiplier value. Okay. Here the given function contains n cube. Say 10 n cube. This contains n cube. But we are trying to bound it using n square. Okay, they are asking us to show 10 n cube plus 20 n is not equal to order of n square. Okay, it would be equal to order of n cube. Then that would be correct. But here the answer is order of n square, which is not correct, right? So this is not possible because n cube grows faster than n square. For large values of n, 10 n cube plus 20 n will exceed any constant multiple of n square. So definitely 10 n cube plus 20 n is not equal to order of n square. It is equal to order of n cube. So Big O is very useful, but it has some limitations. It does not tell exact execution time. It ignores constants, but constants may matter in real systems. Some algorithms are difficult to analyze mathematically. Also, Big O does not consider coding effort, hardware performance, compiler quality, or memory access time directly. So Big O gives a general theoretical comparison, not complete practical performance. To summarize Big O notation, it is used to express algorithm complexity in a general way. It tells how fast the running time or number of operations grow with input size. It gives an upper bound for the growth of an algorithm. For large input values, we ignore constants and lower order terms. So understanding Big O notation helps us compare algorithms and choose efficient solutions. So thank you for watching. Please subscribe to Mana CS Classroom.